Anyway, we've got this week, we've got next week, then we've got spring break. So this is the last week of the first half of the semester. This is week 9. So after this week, we'll be halfway through the second semester. So we're getting there. Going to be honest before I know it. And of course, seniors they get out even earlier. So seniors don't have that long left because they usually get out 2 or 3 weeks before the rest of us, somewhere around there, a couple of weeks. So seniors are really getting excited because they're over halfway already in their semester. So I think we only have like one senior in here though, so we don't have many in this class. So, all right. How many folks we got in here now? Well, a bunch, but not anywhere close to 35. So, well, they'll just have to join us on the fly, I guess. We're not going to wait forever for them. But anyways, so it feels like an empty room today. It's just me and Mr. Granderson here. Mrs. Dean, I don't know. Maybe she's sick. She doesn't hear it all today. I don't know why she's not here. And Mrs. X has a sick kid. She was here for a little while, and then she got a call and had to leave because her kid is sick. So it's just me and Mr. Granderson in this room today. But there's usually 4 of us, but the ladies are out and about. So it's guys' day in the math science room here at Virtual. That's all right. We can handle it. Mr. Granderson and I, we'll hold down the fort. So, okay, well, let's go ahead and put it up. It's 12:54. We've given 5 minutes for all the slackers to get here to class. I shouldn't call them slackers. Yeah, I probably should. We'll give them 5 minutes. That's all right. It's all in good fun, just because they're late. All right. Oh, I didn't want to do that. That's not what I was trying to do. I was just trying to click and get it to quit blinking. All right, Algebra 2. Let's take a look at the grade screen just to see what in the world are we doing. Everything from Module 5 is done. Look, here's Module 5.5 matrices, and we're getting way down at the bottom. In fact, the only thing this shows is a quiz. But we do have some lessons to go through before that quiz because there's some things we need to know that quiz covers that we actually have it covered. So we're going to look at a few lessons today on matrices, and I may even do one of them on paper just because there's something that I see people struggle with every year on this quiz. And it's something that we're covering today that we haven't talked about yet with matrices. So I'm trying to get a blank sheet of paper ready. Okay, I got a blank sheet of paper ready when we're ready to get to that point. But we are in week 26, which actually this is past week 26, but we had that snow week, pushed us back. So this is actually week 27. But we need to go through this folder with these 3 lessons. Intro to zero matrices. That's what people mess up on the test, on the quiz. Properties of matrix addition and properties of matrix scalar multiplication. The properties. We've looked at how to do addition and how to do scalar multiplication. But let's look at these things. This is the properties of intro to zero matrices lesson. So it'll have a link. Click on the link. Take us to Khan Academy. We'll see if I'm logged in. I haven't been on Khan Academy yet this week. Oh, I'm still logged in from last week. It keeps my name up there. So any work I do, it'll keep for me. But this is just a lesson. So let's close the little half tab. We had the full page. Again, it reviews what a matrix is. The rectangular arrangement of numbers in the rows and columns. This is a 2x3 matrix. That's the first thing in every lesson. And it's got links back to intro to matrices and add, subtract, and all that if you forgot how to do that. But let's talk about the definition of a zero matrix. And yes, it is literally what you probably think it is. A zero matrix is a matrix in which all the entries are zeros. Hey, so far so good. This is not hard to understand, right? Here's some examples. A 3x3 zero matrix. We're going to call it O, or and it's 0, 0, 0, 0, 0, 0, 0, 0, 0. A 2x4 zero matrix, 0, 0, 0, 0, 0, 0, 0, 0. So a zero matrix is indicated by O. We just generally name them O because it reminds you of a zero. And a subscript can be added to indicate the dimensions if necessary. So we have a 2x4 zero matrix or a 3x3 zero matrix. So zero matrices play a similar role in operations with matrices as the number zero plays in operations with real numbers. So let's say, what in the world are you talking about? What happens when we add a zero matrix? Recall that to add two matrices, we just add the numbers together, right? So if we have this problem right here, matrix addition, I want to add this 4, 5, 1, 3 matrix to a zero matrix that's also a 2 by 2. So let's take a wild guess. I'm going to open up the chat. What do you think the answer would be adding a zero matrix to 4, 5, 1, 3? Put that in the chat. No change, Jacob says. Still going to be 4, 5, 1, 3. Well, Jacob's absolutely correct. He's right on it. If it's a 4, 5, 1, 3 to start with, and we add 0, it does the same thing that adding 0 does to any other number in math. You got it, Mary. 4, 5, 1, 3, check. There's a little green check mark. Yes, a zero matrix is exactly what you think it is. If you add it to a matrix, nothing changes. The only thing you have to make sure is you're adding the right size zero matrix. We can only add a 2 by 2 to a 2 by 2. So we have to use a 2 by 2 zero matrix. Let's look at the next one. Okay, this is a 3 by 2. So this time the zero matrix is first. So if we have the zero matrix and we add the negative 2, 3, 4, 8, negative 7, 1 to this zero matrix, guess what we get? Negative 2, 3, 4, 8, negative 1, and 7. This should be no surprise to anybody, right? This is very basic. We understand that adding 0 changes nothing, and it's still true even with a matrix. But here's where people get a little confused when we don't actually put the matrix and we just use the letters and stuff. But just pay attention to what they're saying here, and this really makes sense. So when we add an m by n, which is, that's the rows and columns, m by n zero matrix to any other m by n matrix A, we get matrix A, right? If we have a matrix plus a zero matrix, we just get whatever the matrix was, matrix A, or a zero matrix plus A, we just get matrix A. And here the dimensions are not specifically given. We don't know what size these are, but we just have to understand that the dimensions have to be the same, right? If that's a 4 by 2, then they're both 4 by 2. If that's a 1 by 5, they're both 1 by 5. That's just the way that matrix addition works. So here's a reflection question. What are the dimensions of the zero matrix in this equation? B plus O equals B, given that this is B. So tell me, what size is the zero matrix that we're going to add to matrix B? This is a good check just to make sure we're still thinking right about dimensions. What are the dimensions of the zero matrix that we can add to matrix B? Right here, it's waiting on the dimensions. Same dimensions of B. All right, what are the dimensions of B then? Because some people still get that confused. That's why I'm asking that, because some people still get that confused a little bit. It's like, what is this? Is this a 3 by 2 or a 2 by 3? Yeah, it's one of those. This is either a 3 by 2 or a 2 by 3. Yeah, rows come first. So you guys you're thinking well, right? 2 rows, 3 columns. Always count the number of rows up and down. This one has 2 rows and 3 columns. Check. That's absolutely correct. Now let's look at this. What happens if we add an opposite matrix? The opposite of matrix A is the matrix negative A, where each element in this matrix is the opposite of the corresponding element in matrix A. For example, if matrix A is this, 4, 1, negative 6, and 2, then negative A is negative 4, negative 1, positive 6, and negative 2. That kind of makes sense? You see what they're doing? how we create negative A. This is really scalar multiplication because negative A means we take A and we multiply it by a -1. That's what negative A is. It's -1 times A. So we just take every element and multiply it by -1. So let's look at this matrix addition problem. 4, -3, 8, and 7 added to -4, 3, -8, -7. What's the answer going to be for adding these opposite matrices together? There he says it's O. It's the zero matrix. It's the O's, the zeros. Yeah, absolutely, because 4 plus -4, -3 plus 3, 8 plus -8, 7 plus negative, they're all going to equal 0. So it gives us the zero matrix by adding the opposite matrix. So let's look at this one here. -4, 2, 5. Same thing. 4, -2, -5. See, everything over here has just been multiplied by -1. So we should get another zero matrix. That quick and easy. Check. All right, so the conclusion to this lesson. So if we add any m by n matrix to its opposite, we get another m by n zero matrix. It's going to be the same size because we know adding keeps the same size. So if A is any matrix, then A plus -A equals O, the zero matrix. And -A plus A equals O. It's also true that A minus A equals 0. So this is why, because subtracting is like adding the opposite. It's the same thing, right? If we need to take 4 minus 4 or 4 plus a -4, so we either subtract or add the opposite and get it 0. What happens when we multiply a matrix by the scalar 0? All right, so when we have this, we've got 0, which is just a scalar number, times 5, 4, 9, 1. Remember how scalars worked? We just got through doing scalars last week, scalar multiplication. You take whatever number's out front, in this case 0, and you multiply it by each element individually. 0 times 5, 0 times 4, 0 times 9, and 0 times 1 is 16. Just making sure you're awake. 0 times 1 is not 16. It's also 0. So scalar multiplication works just like any other multiplication. 0 times anything is 0. All right, 0 times anything is 0. So it doesn't change with matrices. It's the same thing. I need help. What can we need help with? Oh, it shows us the answer. Okay, it shows us the answer because that'd be 0 times 5, 0 times 4. 0. All right, got it. Thanks. Here's another one. This is a 3 by 3 matrix, and we're multiplying it by a scalar 0. No surprise. It's all zeros because multiplying anything, any number times 0 will give us a 0. Get a little check mark. When we multiply any matrix by the scalar 0, no matter what m by n is, we get an m by n 0 matrix. So that means 0A equals O, the 0 matrix. All right, so summary. Let's compare the 0 matrix to the real number 0. We said above that the 0 matrix behaves just like the real number 0. So that means we can make these connections. Adding 0 to any number A gives you back the number A. It means A plus 0 equals A, and it doesn't matter what number A is. A could be a million. A million plus 0 equals a million. -7 plus 0 is -7. Doesn't matter what A is, add 0 to it, you'll get it back. With a 0 matrix, adding a 0 matrix to any matrix A gives back the matrix A. So if we have a matrix named A, regardless of what size it is, 2 by 3, 5 by 8, doesn't matter. and we add the 0 matrix to it, it will just give us the original A matrix back. Okay, that makes sense. We just looked at that. How about this? Adding any number to its opposite will give 0. A plus negative A. So if A is 10, this would be negative 10. If we add 10 to negative 10, it's going to give us 0. Okay, that makes sense to us. We've seen that since we were in elementary school. Adding any matrix to its opposite will give a 0 matrix. So matrix A added to the opposite of matrix A, which is all the same numbers, just different signs, will give us the 0 matrix of the same size. Whatever size A is, the 0 matrix will be the same size. Any number times 0 is 0. A times 0 equals 0. Yes, we've known that since elementary school as well, right? Any number times 0. 2,841 times 0 is 0. Same with scalar multiplication. If we put a 0 times any matrix of any size, we'll get the 0 matrix of that same size. So understanding these connections can make matrix calculations involving a 0 matrix much easier. All right, so that is the end of that assignment. Let's go back and see what else we need to investigate. Properties of matrix addition. Again, we've looked at matrix addition. Let's look more closely at the properties that we used to do it, because we might not have thought about the properties. All right, again, I'm going to close this little half tab because it gets my way and annoys me. In the table below, A, B, and C are matrices of equal dimensions. Okay, so they're saying right now, whatever size matrix A is, B and C are exactly the same size. They're all 4x2s or 1x5s or 3x3s or whatever, but they're all the same. They're all the same. So with that being all the same, and again, we're going to look at the quiz because the quiz has a problem like this that people get confused about. Looking at these properties and the 0 matrix. So the commutative property of addition works with matrices the same as it does with any other number. And you're like, what do you mean it works the same as any other number? Well, let's look at this. Look at this. This says that according to the commutative property, matrix A plus matrix B equals matrix B plus matrix A. So I want to put this up. It says matrix A plus matrix B is the same as matrix B plus matrix A. That's the commutative property. And we've known that forever because we said, well, if we add 3 plus 8, that's the same thing as 8 plus 3. It really doesn't matter in mathematics which number we put first if we're just adding them together. So that's also true with matrices. It doesn't matter which order they're in, it's going to be the same answer. So that's what that's talking about. What else is it saying here? It's saying the associative property. A plus B plus C is the same as A plus B plus C. So it's like, okay, what? Associative, let's write that out. So it's saying if we take matrix A and matrix B and matrix C and we're adding them all together, we can add these together first, B plus C, and that will be the same thing as if we added A plus B together first and then added C. And that's the way we've always known how math works. You're like, what? Well, if I add 3 plus 7 plus 9, I'm going to get, let's do this, 3 plus 7 plus 9. It doesn't matter if I add these together first and do 3 plus 16, or if I add these together first and do 10 plus 9. Either way, I'm going to get the same answer. They are equal. It doesn't matter. I can add these together first and then add to the other one. Or I can add these together first and then add it to the other one. But it's the same. So it's the exact same with matrices. If you have 3 matrices, add 2 of them together first. It doesn't matter which ones. You can even add A and C if you want. 3 plus 9 is 12 plus 7. It's still 19. It doesn't matter what order you add them in. If you're just adding three together, do it in whichever order you want to, because it's all the same. It's equal. The additive identity property. For any matrix A, there's a unique matrix 0 such that A plus O equals A. So what that is saying, because that's kind of wordy, it says A can be anything. It can be a 1, 2, 3, 4. It could be a 1, 2, 3, 4. Doesn't matter what A is. There is a 0 matrix that we can add to it and get A to it. In this case, we could add a 0, 0, 0, 0. There is a matrix O that exists. We could add a 0, 0, 0 matrix. There are 4 zeros. It doesn't matter what size A is. We can add a 0 matrix to it that's the same size and end up with the original A. That's what that's saying. So don't let the wording confuse you. It just says whatever size A is, we can add a 0 matrix to it, because 0 matrices can be any size. Any size you want. Additive inverse. For each A, there's a unique matrix negative A, such that A plus negative A equals 0. I don't know if I need to illustrate that, but that works just like math. If we pick a number, 437, and we add to it the negative of the same number, we can get 0. Same thing with matrices. Any matrix A, there exists a negative matrix A that we can add to it and get 0, the 0 matrix. It's just saying, doesn't matter what it is, just pick one, but you can get the 0 matrix. And closure property. A plus B is a matrix of the same dimensions as A and B. Let's talk about the closure property real quick, because that's something that's interesting. The closure property says if A is a 1, 2, 3, 4, 5, 6 matrix, and B is a 7, 2, 4, 3, 9, 0 matrix, this is a 2 by 3 matrix. This is a 2 by 3 matrix. The closure property says has to be a 2 by 3 answer. That's what the closure property says. I don't need the little thought in there. The closure property says if I take a 2 by 3 and add it to another 2 by 3, the answer has to be a 2 by 3. It's like a closure. I can't pick out an answer that's a different size. It has to be the same. I can't add a 2 by 3 to a 2 by 3 and end up with a 4 by 1 answer. It's just not possible. That's the closure property. So this article explores these matrix addition properties. So again, it reminds us that a matrix is a rectangular arrangement of numbers. To add two matrices of the same dimensions, because that's the only way you can add them, just add the numbers together. 3 plus 5, 7 plus 2, 2 plus 8, 4 plus 1. If any of this is new to you, review these other lessons we've already looked at. All right, dimension considerations. So notice that the sum, remember the sum is when you add things, of two 2 by 2 matrices is another 2 by 2 matrix. So in general, two m by n matrices is another m by n matrix. This is the closure property that I was just talking about. There's no way you can get anything else. If the two dimensions of the matrices are not the same, addition is not defined. You cannot add them. There's no definition for how to do that. If A is a 2 by 3 matrix, B is a 2 by 2 matrix, you could add 2 to 5, 7 to 2, but what do you do with the 8? There's not a number to add the 8 to. So that's why it's not defined, because there's no possible way the 8 and the 3 get left out over here. It wouldn't make sense to add it to any of these other numbers, because they're already adding to these numbers. So matrix and real number addition. Because matrix addition relies heavily on the addition of real numbers, many of the addition properties known to be true are also true with matrices. So again, looking back at that commutative property, A plus B equals B plus A. That's true with numbers. 3 plus 8 equals 8 plus 3. So it's also true with a matrix. So here, let's look at this example down here. If we have 3, 7, 2, 4 plus 5, 2, 8, 1. We could take 3 plus 5. Oop, the whole thing lights up. 3 plus 5, or we could take 5 plus 3. It doesn't matter. 3 plus 5 or 5 plus 3. Either way is going to get you the same answer. 7 plus 2 or 2 plus 7. 2 plus 8 or 8 plus 2. 4 plus 1 or 1 plus 4. Either one, you're going to end up with the same thing. And so it's the same as adding it the other direction. The 3724 could be first, or the 3724 be last. Doesn't matter. The associative property, where we talked about A plus B plus C is the same as A plus B plus C. It doesn't matter which ones you do first. So let's look at this matrix example. So here is matrix A, B, and C. And here they take A and B and add them together first. So you've got 5 plus 3. That's 5 is the first element there, 3. And then the 1's over here. So 5 plus 3 plus 1. Over here, they took the 5 by itself and added the 3 and the 1 first. 5 plus 3 plus 1. So this would be 8 plus 1. This would be 5 plus 4. Either way, they're going to equal the same number. So we're happy with that. We understand how that works. There's the additive identity. It means we can get a zero matrix the same size as any matrix and end up with that same matrix unchanged. 3, negative 1, 7, 9 added to a zero matrix is 3, negative 1, 7, 9. And it doesn't matter if the zero matrix is first or second. Adding it to it does not change matrix A. And then the additive inverse, where we can, any matrix, we can take the opposite matrix. So if we have negative 2, 8, negative 3, 1, the opposite matrix would be a positive 2, negative 8, positive 3, negative 1. Exact same elements with the signs reversed. And anytime we add those together, negative 2 plus 2, 8 plus a negative 8, negative 3 plus 3, 1 plus a negative 1, we get a zero matrix. All right. Oh, these are the type of questions I like, because it's the type of question we have in the quiz, and we need to practice this because people get confused. For the problem below, let A, B, and C are all 2 by 2 matrices. Okay, so that's what we understand first off. All of these are the same size. So which is equivalent to this? Choose all that apply. So, all right, I'm looking in the chat. Class participation here. If I have A plus B plus C, which of these is equivalent to that? Which ones will give me the exact same answer? And there may be more than one. A, B, C, and D very well could be more than one answer. So which of those are equivalent to A plus B in parentheses added to C? Either you all really like the alphabet or you're saying it's the first 3 answers. A, B, C. Okay. A, B, C. I think y'all are choosing the first 3 answers and not trying to brag about your knowledge of the alphabet. No one thinks D, huh? A plus C in parentheses plus B plus C in parentheses. Yeah, you're right. That's not going to work because C is being added twice. I mean, think of it with just regular numbers. 1 plus 2 plus 3. This would be 1 plus 3 plus 2 plus 3. That wouldn't be the same as 1 plus 2 plus 3 or 3 plus 1 plus 2 or 1 plus 2 plus 3. Okay. All right. Great job. Correct. Ooh, this one's a little tougher. This is our last one on this lesson. Which of the following matrix expressions are equivalent to, oh, gotta look closely, A plus negative A, all in parentheses, plus B, and they're all the same size. They're all 2 by 2 matrices. They're all 2 by 2 matrices. So which of these are the same as what that is? A, B, C, and D. And they're all, and this is important to know, they're all 2 by 2 matrices. Are we on the ABC kick again? ABC, that's what people are saying. Surely you're not just now answering the last one. I'm going to say you're answering this again. So let's see. A plus negative A. Well, we know that should be a zero matrix, right? A zero matrix plus B. So a zero matrix plus B, that would just be B. That should be the same. That should be equivalent to just B. Or we could add the negative A to the B first and then add A to it. And as we looked up above, that should be the same. Just moving the parentheses, what we add first shouldn't make a difference. And A plus a negative A should be a 2 by 2, since these are both 2 by 2s. It should give us a 2 by 2 zero matrix, which we can then add to B. It will not give us a 3 by 2 zero matrix because they are defined to be 2 by 2 matrices. So I think you're right again, guys. Look at that. Perfect. A, B, C. And that's the end of that. Okay, let's go back and see the last lesson we're investigating today. Properties of matrix scalar multiplication lesson. Let's see these properties. So everyone having a good day? How are things for you now? Oh, wait, here comes something. Okay. It goes over properties here with multiplication. So on the table below, A and B are matrices of equal dimensions, and C and D are scalars. Okay, so C and D are not matrices, they're scalars. O is the zero matrix. So here we go. C times D times A is the same thing as C times D times A. We can multiply the scalars together first and then multiply it times the matrix. Or we can multiply one of the scalars times the matrix and then the other one times the matrix. That works either way. The distributive property says if we're taking this scalar times A plus B, that's the same as taking the scalar times A and then the scalar times B and add them together afterwards. So we can either add A plus B together before we multiply or multiply times each of them individually and then add. And C plus DA is the same way. We have two scalars. We can add them together first and then multiply them by A, or we can add them, multiply them individually times A and then add the total. The multiplicative identity property. Identity property says if we multiply something times 1, you end up with the same thing, right? 1 times 31 equals 31. 1 times 1/2 equals 1/2. If you multiply something times 1, you'll not change anything. You'll get the same number back. And that's the same thing with matrices. Multiplicative identity property. Scalar of 1. Multiplicative properties of 0. 0 times a matrix will give you the 0 matrix. Any scalar, any number times the 0 matrix will also end up with a 0 matrix. So we can multiply a 0 matrix times 74. And we'll end up with just a 0 matrix. Closure property multiplication. So C times A is a matrix that has the same dimensions as A. So if A is a 3 by 3 matrix and we multiply it by any scalar, our answer is a 3 by 3 matrix. There's no possible way to get a 2 by 4 matrix or a 5 by 1 matrix or any other size than the exact same size it started. So let's look into more details. Scalar multiplication refers to the product of a real number times a matrix. All right, so let's see. Dimension considerations. Notice that a scalar times a 2 by 2 matrix is another 2 by 2 matrix. In general, a scalar multiple of a matrix will be another matrix, same dimension. A scalar does not change the dimensions of the matrix. It's what I meant by the closure property. It has to be the same. It will not change it. Because scalar multiplication relies heavily on real number multiplication, many of the multiplication properties we know to be true with real numbers are also true in scalar multiplication. So, associative property of multiplication. This says if a matrix is multiplied by 2 scalars, you can multiply them together first and then multiply by the matrix, or multiply the matrix by 1 scalar and then the resulting matrix by the other. So let's look at this with C equals 2, D equals 3, and A equaling this matrix. So this way, where we multiply the matrices together first, 2 times 3 is 6. So you have 6 times 5 is your first term. And 6 times 5 we know is 30. We did it this way and we multiply the 3 times the matrix first. You get 3 times 5, you get 15. And then you multiply it by 2. So 2 times 15 is also 30. So we got the same number over here as we did over here. Let's look at the second one. So 2 by 3 is 6 times 4. So 6 times 4 is 24. Over here, we're taking the 3 times 4 first, so that's 12, and then multiplying by 2. What's 2 times 12? It's also 24. And that's going to work for all 4 elements of the matrix. Doesn't matter which order we do that. In each column, we simplified one side of the identity into a single matrix. And the 2 matrices are equal because of the associative property of multiplication for real numbers. We take 2 times 3 times 5 or 2 times 3 times 5. Either way. Distributive. So this says that a scalar can be distributed over a matrix addition. See, and I'll illustrate that. We know that's to be true as well, because if I have 3 times 2 plus 5, I can take the 2 plus 5 first and then multiply it by 3. Or I could take 3 times the 2 plus 3 times the 5 if I wanted to break them out first instead of adding the inside together. 3 times 2 is 6. 3 times 5 is 15. Either way, it ends up the same number. So it doesn't matter when you have distributive property there where you got parentheses, if you distribute first or if you do everything inside the parentheses first. And that's what this is saying. We can add the 2 matrices together first and multiply by a scalar, or we can just take the scalar times the first matrix and the scalar times the second matrix and add them together. So add these together. 5 and 3 is 8 times 2 is 16. So 2 times 8 is 16. Over here, we took 2 times 5, which is 10. We took 2 times 3, which is 6. And we add together 10 plus 6, 16. Same number either way. So we know that works. And it works the same with 2 scalars in one matrix. See, this is 1 scalar in 2 matrices. Same thing if we reverse it. We could add the scalars together and multiply, or we can multiply first scalar and then the second scalar and add them together. So I'll skip down here. Multiplicative identity property. 1 times a matrix equals the matrix. 1 times 2, 5, 1, 7 is 1 times 2, 1 times 5, 1 times 1, 1 times 7. It's 2, 5, 1, 7. It's exactly what we started with. That's not a surprise either. A lot of this is really, really that simple. Just read these problems carefully when you take the quiz, because I want to see you really kill it. Multiplicative properties is 0. 0 times any matrix is the 0 matrix, right? 0 times this 3, 8, 6, 7. 0 times 3, 0 times 8, 0 times 6, 0 times 7. You're going to get a 0 matrix the same size as the original matrix. All right, here's our check our understanding. Which of the following are equivalent to C times 1A plus B? I think I'm going to make this a little bigger because we're getting some interesting stuff here. I'll make sure you can see that clearly. Which of the following, let's see, did it tell us the size? Oh, these are all 2 by 2 matrices. A and B are 2 by 2 matrices. So which of these are the same as this? There could be more than one. And we have 3 choices this time. Daniel's quick on it. And people agreeing. I don't see anyone saying A. Well, let's look at A and see what's wrong. So this says C times 1A plus B. Well, we know 1A just gives us A. That doesn't change anything, right? Multiplying it by 1. So this is really just A plus B. So if we add A and B together and then multiply it by C, okay? And this is saying 1A, which is to say times C, and then just add B to it. Well, that's not the same because C has to be multiplied by both of those according to the distributive property. So we can't just multiply it times the first one. So you're right. A doesn't fit. CA plus CB. That's just distributing the C times 1A and C times B. And since 1A is the same thing as just A, that is the same thing. And this is just the opposite of this. And we already know that adding 3 plus 8 is the same as adding 8 plus 3. So that should be good. Check. Marvelous. All right. Let's see. This is our last one here. Which of the following are equivalent to CD? We got two scalars. CD times A plus 0A. BC again. So A says it's just equal to A, and everything else cancels out. B says you can take D times A and then multiply that by C, and that'll be the same. So that's a lot different than answer A. C says we can take CD and add 0 to it and then multiply it times A, which if you distribute that, that would be A times CD and A times 0, which, basically they just factored out an A. If we look at the original problem, CDA plus 0A, if they factor out A, it's CD plus 0A. Yeah, that is the same. They just factored out the A. CDA plus 0A. The 0 times A is just going to be a 0 matrix. It's not going to change anything. So when we add it to this, this is all the answer going to be. So it is CDA, because this is going to be just 0. It's not going to change anything. And yeah, this just ignores the fact that we have a C and a D. So unless C and D are both 1, this one is wrong. All right, very nice. Okay, so we have looked at the 3 lessons. So let's look at the quiz and see what all it contains. You have 3 attempts. All right. I want to look at, this is not even showing me the whole problem. Oh, there's an error there. Hopefully it doesn't happen with you. It didn't load my image. If it doesn't load your image, then I'll go back and look at that and give you credit for that problem. Yeah, it broke. It's 404, and something happened with that image. It got deleted or moved. So nobody may be able to do 3. If not, I'll give you credit for 3. I'll give you that. But let's look at these, because these are a little different. If A, B, and C are 5 by 5 matrices, and O is a 5 by 5 0 matrix. Okay, so all these matrices are the same size. Which of the following is false? A, B, multiplying A times B is the same as multiplying B times A if they're the same size matrix. A times B times C is the same as A times B times C. A times parentheses B plus C is the same as AB plus AC. 0 matrix times A times B times C equals the 0 matrix. Or they're all true and none of them are false. So think about those very carefully going through. Are any of those false, or are they all true? Is there one? And let me check more than one. Oh yeah, you can pick multiple answers. So go through them one by one and say, is this true? Is this true? Is this true? Is this true? If they're all true, then you're choosing that. But if there's any that aren't, go through that. Okay, this one gets a little tricky. So think about that. This is really tricky. A, B, and C are either, so it could be either one, identity or 0 matrices. Identity or 0 matrices. I feel like I need to define that to remind us, because we haven't done it about identity matrix, 0 matrix. Identity matrix is basically multiplying times 1. That's what an identity matrix is. It just multiplies by 1, so you end up with the same thing. And this one is multiplying 0, so you end up with the 0 matrix. So this is saying, I'm gonna turn it over and write this. A times this matrix, whatever this matrix is, plus B times this matrix, and they're different matrices, minus C times this matrix equals, and then it's got numbers over here. So I'm going to just do the first number on looking at this, because it should tell you everything you need to know. Okay, this is what their first problem is. And I didn't write the whole matrix. I just wrote the first number, so I don't want to get confused. So something times 2 plus something times -3 minus something times 1 equals 1. So you have to figure out A, B, and C. Is it an identity matrix, which means it's a 1? Or is it a 0 matrix, which is a 0? So where would I put 1s and 0s for this to be true? Like if I made them all 1s, I said they're all identity matrices. Well, that would be saying 2 plus 1 times -3. So it'd be -3 minus 1 times 1 minus 1 equals 1. Is that true? 2 minus 3 minus 1. No, that's -2 equals 1. That's not true. So these are not all 3 identity matrices. At least one of them has to be a 0 matrix. At least, maybe more than one. At least one of those. So figure it out. Figure out, replacing those with 1s and 0s, which A, B, and C is A an identity matrix, B identity matrix, and C a 0 matrix? Or is A an identity matrix, B is a 0 matrix? You know, that's what you're trying to figure out. And what does the question ask? It asks A, B, and C are either identity 0. Which of the matrices must be identity matrices? So this one's asking, now watch, yours may be phrased differently. Mine says, which of these must be identity matrices to make the following equation true, which means the ones that aren't are 0s automatically. So if I decide that B and C are both identity matrices and A is a 0 matrices, my answers are B and C, because it's just asking me which ones are identity matrix. It may ask you which ones are 0, so read it carefully. And no, I don't think B and C is going to work here, but I'm just showing you how. I'm not giving you the answer. I'm just showing you how to figure that out, because people really struggle with this one sometimes. This one's not loading it, so again, just put 999 and I'll count it right. Or whatever. If you've already turned it in, I'll go back and count it right for number 3. And A, B are 2 by 2. C is a scalar. Which of these are equivalent to C times 0A plus B? That's like the ones we were just doing on the screen. So only 4 questions. So that's only a 20-point quiz. We don't have a whole lot on there. It's just a 20-point quiz. But this will wrap up matrices. We'll jump into something for 1 week before we go to spring break. So we'll have just one thing next week just to look at before we leave for spring break. Maybe 2 lessons or 1 lesson. I haven't even looked ahead that far yet, but I will be as the week goes on here. So anyway, any thoughts, any questions on any of that? That's all we have. Just the matrix quiz too, but it's all about these properties that we looked at this week. So we had to go through all those properties and understand that. Now, if you're missing any other matrix assignments, get those done. Easy. I've seen a lot of grades come up during this because it's not too difficult. This is probably the trickiest thing we had is these properties. This is the trickiest thing we've had. The other matrix equations were pretty simple, and people have raised their grade during this unit, and I always love to see that. Like I said last week, nobody is failing this class right now. Let me see, is that still true? After last week's grades were updated, which means if you're failing now, it means you didn't do your last week's work. But let me look. I have 1 person that's below 60 because they didn't get last week's turned in. They're behind. They're behind. The zeros are adding up and bringing their grade down. So get these turned in. Get your grades up, guys. I'll try and get it updated first thing in the morning or something. But when you're doing your grade check, you can always look and buzz. That's your most accurate grade. I don't mind that. But anyway. All right. If you got questions, hang around. Otherwise, you got enough time easily to finish this 4-question quiz before your next class. So you can be done for the week because you just have one thing in here this week, just the quiz. But if you're behind, by all means, get those turned in. But anyway, have a great week. I'll be here Wednesday only because it's a B-Day Friday.